Okay. All right. So this chapter, NP-completeness, will be the last lecture of this semester's course, okay, of this whole course. And I choose to use this chapter as the ending one because it's not about a specific kind of algorithm, but it's a more high-level theoretical framework that studies the properties of algorithms. And the main property that this theory is trying to describe about algorithms is actually how difficult algorithms are. If we want to say it with plain language, it's about how easy or how difficult an algorithm is to solve, to get a solution of it. Okay, so it's a very high level description of algorithms. Okay, so we had some ideas about how we describe an algorithm in terms of running time, right? That is what we started doing from the second second lecture of this course, right? We defined a series of asymptotic notations using big O, big theta, big omega, small omega, and so on to describe the running time of algorithms. And also we had quite a lot of experiences now about what kind of running time efficiency that we are looking for. If we want a solution, if we want an algorithm to be reasonable, to be reasonably fast, or at least it's at an acceptable running time, right? And we know that how to, given for example, two variations of the same algorithm that solve the same problem, we are actually able to compare the two by looking at the running time efficiency of both, right? To see which one has a better running time property, which one whose function runs slower or versus the one that runs faster. Okay. So the topic of NP-completeness is basically built upon the concepts of the difficulty of algorithms and using the notations, using the asymptotic notations that describe the running time of algorithms. And it's actually at a higher level. So let's start from some concrete example, like to look at what kind of problems that we should consider easy versus difficult ones. Okay, so we have just done with the shortest simple path in the graph, right? So if we switch the term from shortest to the term longest, then it will be a totally different problem. Okay, we can actually write, given a graph, if we run Bellman-Ford on it, right, we can actually get a shortest path for each vertex in a graph within big O of V times E time, big O of V times E time, right? Right. So if that is the shortest path problem, but if it is the longest simple path that we want to find, even if it's between two vertices, then it will be a very difficult question. Okay, so you can think of it. Why, right? Because we want to find the longest, then we basically need to go through a lot of possible paths, right? We want to basically enumerate all possible paths between two vertices. And that is quite a lot of time, quite a lot of possible ways to go, right? We can choose the longest path to go. Then that is a very, very difficult one. There's a way lot of possible So it's like at an intersection, there could be a lot of ways to go because there's no upper limit to the total number of weights that you can for total weights of paths that you select. Okay, so actually merely determining whether a graph contains a simple path that is above some threshold with at least a given number, right? Even to determine this lower bound is a very hard problem. Okay. All right. So that's one one example, okay, of the how hard or versus how easy problem. And the second example I put here is the I think it's also related to the graphs, okay, to the graph algorithms. The one problem is called a Euler tour, okay, or Euler path of a graph, okay. So that means we want to traverse a graph with a cycle that each edge is visited exactly once. Okay, so I think that is a type of geometric problem that we had some experience with, right, in high school probably. So it's like we want to go through each edge exactly once, and we want to go back to where we started, right? Go back to the vertex that we started. Okay, so this is a interesting problem that actually can be determined by basically you count how many edges are connected to each vertex, and you basically count how many, whether that number is an even number or odd number. Okay, I think the principle is that you basically need to. There are two cases that satisfy this Euler tour problem. So either you have all the vertices with even number of edges connected to it, or you only have two vertices that have odd number of connection, while all the others are even numbers, right? So only in these two conditions you can satisfy that a graph, a Euler tour problem is solvable. Okay, and that means that the problem is actually quite easy. Okay, we just need to basically count the number of edges, right, for each vertex, right? So it's basically a big O of E time, running time algorithm, right? But if you look at a slightly different one, a Hamilton cycle of a graph is a cycle that visits the vertex exactly once. Okay, so it's a bit different now. It's not about edges, but about visiting the vertices. And it turns out that actually, for example, in the pictures here, we follow this path to visit each vertex exactly once, right, within a Hamiltonian cycle. And it's actually quite a difficult one. To determine whether a graph has such a solution is very hard. Okay, it's like we have to do a lot of computation, and that amount of computation is way more than the big O of. Okay, so these are all known facts, existing facts about very similar problems that look similar but are actually requires very different amount of time to be solved. Okay, so the third example, it's not as straightforward as the previous two examples, but I listed here because this conjunctive normal form problem is a formal way to prove the difficulty of different types of problems. Okay, so after we have defined the CNF problem here, actually basically any other kinds of different problems can be converted, can be reduced to such a type of problem. Okay, so we can, if we can prove that the CNF is so if we can prove that any type of problem is at least as difficult as CNF problem, then we can use the CNF problem to determine the to define the difficulty of that problem. Okay, so we'll see that later, but let's go through this problem first. Okay, so it's like a Boolean formula. Okay, so a Boolean variable is a binary variable. It's whether 0 or 1. Okay, so a formula that consists of Boolean variables, the final value is also binary. It's also either 0 or 1. Okay, and we will use the Boolean operators like and, or, and not. Okay, so we will say that if we have a formula, right, we will say that formula is satisfiable. Okay, if there exists some assignments of the 0 and 1 values to its variables and cause the whole formula will evaluate to 1. So if we can do that, then we will say the formula is satisfiable. Okay, so we have the 2 conjunctive and the 3 conjunctive. Basically, we can define a K conjunctive normal form, which is K CNF. Okay, and if the formula looks like it is connected by and of ors, okay, so it's like a series of and of ors, and what's within the ors is actually K variables. So if the formula looks like this, then we say it's KCNF. So let's see some concrete example. A 2CNF will look like this. Okay, so it's a series of ends. So this is the end, right? We have 2 ends that connects 3 ors, right? So within here, it's a or, and within each parenthesis, it's a or connection. Okay, and between the or, there could be some variables, or the negation of the variables. That doesn't matter. Okay, so as long as the formula looks like it's a series of and of ors. Okay, and in this case, the ors are connecting 2 variables, so it's a 2CNF problem, right? There's 2 variables, x1, x2, not x1, x3, not x2, and not x3, right? So it's like 2CNF problem. And like we can easily get the definition, like we can solve it, right? Basically, if we let x1 to be 1, x2 to be 0, and x3 to be 1, then the whole equation here will evaluate to 1, right? That's something you can examine yourself following the principles of Boolean computation. It's like 1 and 1 equals 1, and 1 and 0 equals 0, and so on. Okay. All right, so that's a CNF. So actually, a 2CNF problem can be solved within a polynomial time. Okay, so a polynomial function is like n to the power of some constant p, right? It could be n squared, it could be n to the power 3, n square roots, right? So anyway, it's a polynomial function, and the n is the how many, for example, how many variables you have, right? All right, so that is a 2CNF, but it turns out that a 3CNF satisfiability problem is not that easy to solve. Okay, it's not as close, not even close to the 2CNF problem. It's a very difficult one. All right, so for example, this one, it's a very simple 3CNF problem, right? It has one end that connects 2 ors, right? And within each or, there are 3 variables, right? 1, 2, 3, connected using to us, right? And actually, it's not that easy to find a solution as compared to the 2CNF problem. Okay. All right, and that's all the examples we have. So we can basically, well, at least what theoretical computer scientists have done is that we classify all the problems in the world into 3 classes. Okay, so let's lay out the definitions first. So the first class is called P. Okay, and this P means the letter P means that those problems are solvable in polynomial time. And the meaning of polynomial is something we explained, right? It's basically n to the power of something constant. Okay, as long as we can solve the problem within that polynomial time, then we say this type of problem is class P. Okay, and right. And the second is NP. Okay, so it's not, the meaning of it is not as the name indicated. It's not, it doesn't mean that it's not solvable. Okay, but it actually means that, I think this is where where the first confusion would come from, right? So the NP is not for not solvable. Okay, it actually means that it's verifiable in polynomial time. Okay, so the action of solving something is different from verifying some solution. Okay, and actually verifying some solution is much easier. Okay, so to verify a solution means that if we give a solution to the problem, then we can actually verify it. We can verify if this is correct in polynomial time. Okay, so for example, in the Hamilton cycle problem, for example, right? The problem asks for a solution that it asks for a path that go through all the vertices exactly once, right? So that is the target solution we want to find, right? So it's hard to solve this problem, right? It's hard to really find one solution that's correct. But for example, if I were given a solution, for example, somebody give me and he claimed that this is the correct one, then we can basically follow that path and examine whether each vertex is visited exactly once, right? But we just need to go through that path once, and then we will know whether this is the correct solution or not. Then it looks like a pretty easy way. It looks like a pretty easy way to verify, right? So if we can verify it within polynomial time, then we say this type of problem is NP. Okay, so that's how we define the P and the NP. Okay, and the last one is the NP-complete. Okay, so it's actually a problem that's within NP, and it's as hard as any problem in NP. Okay, or you can say that NP-complete problems are those hardest among the NP problems. Okay, so the Hamilton pass problem is one of the NP-complete, one of the most famous NP-complete problems. And actually there are tons of other different NP-complete problems. And here the definition is not that strictly separating NP-completeness from NP, because that is not the relationship between NP and NP-completeness, NP-complete problems is not concluded yet. Okay, it's still a open scientific question. Okay, so what we can conclude from the take-home message is that from this slide is that NP-complete is a type of NP problem that is very hard to solve, and it is very likely that this NP-complete problem don't have a polynomial time solution. Okay, although people have not proven it yet. Okay, but it's a typical guess. Okay, so these are the three types of algorithm problems that we can categorize them into. Okay, and actually, the status of the NP-complete is still unknown. Actually, so people have not find any polynomial time algorithm to solve the NP-complete problem. Okay, but nor has anyone been able to prove that no polynomial time algorithm can exist. Okay, so it's like people try to solve the NP-complete problem within polynomial time, but people never succeeded. But also people have never, in theory, proven that there's no such a polynomial time solution. Okay, although it's like people can guess about, scientists have a lot of some guess that they think it's a reasonable guess about the relationship between NP and NP-completeness. So we can go through some of those guesses here, right? But the statement in here in this box is basically the current status. Okay, so no one has solved any NP-complete problem with polynomial time, nor has anyone been able to prove it doesn't exist. Okay, so if somehow you can find a polynomial solution to any NP-complete, anyone can NP-complete problem, you basically solve all the NP-complete problems. Right, so because you will see that the difficulties of different NP-complete problems, they are actually dependent on towards each other. Okay, so we can use the 3CNF to define any type of NP-completeness, NP-complete problems. Okay, so let's carry on and talk about some relationships. Okay, all right. So yeah, so if we want to say describe the relationship in a plain language, right, we can say that if a problem belongs to class P, then we say that the problem can be solved very quickly, right? Otherwise, if it's NP, then it's can be verified very quickly, okay? But it's usually more difficult to solve a problem from scratch, other than to verify a clearly presented solution. Okay, so a typical guess, or most common guess about the solution of about the relationship between P and NP is that we would rather believe that the two sets of problems P doesn't equal NP. Okay, in another way, in another language, NP cannot be solved within polynomial time, right? But that is still a theoretical guess. Okay. All right. So if we take a look of any algorithms that have been so far covered in our course here, they are actually all in the class P, okay? Because the solutions that we come up with all have a polynomial time, or bounded by a polynomial time function, right? Like the sorting problems, like the optimization problems, like the graph problems. We all have a clearly defined running time upper bound that can be bounded by some polynomial functions, right? Right. So that is a typical, that is a some common sense about algorithms that we learn about. And we are actually the majority of work done in designing algorithms is within the realm of polynomially solvable problems. That's within the class P. Okay, for the NP problems, then it's because it's hard to come up with a solution, then we basically need to use a different way to tackle the problem, right? We either simplify the problem, or we ignore some accuracy, ignore some correctness, right? We can tolerate some errors in the solution, but it should be efficiently executable algorithms, right? Otherwise, there's no way to solve a NP-completeness problem within within a reasonable amount of time, right? Okay, so the typical guesses about the P and NP, as we said, that's so first of all, any problem in P is also in NP. Okay, so that is a fact. Okay, so this is not a guess, but this is a fact, because if a problem can be solved within polynomial time, then given any solution, it's of course always verifiable within polynomial time, right? And the next one within the box, it's our current guess. Okay, so the theoretical computer scientists would most commonly believe that the P should be a subset of NP. Okay, although it is still an open question, but the majority of researchers would believe that it is a subset of P is a subset of NP. Okay, and if any NP problem, if any NP-complete problem can be solved in polynomial time, then every problem in NP will have a polynomial algorithm. Okay, so that's why also partially why this type of study are fascinating, because it's like if you get a solution to one of the problems, you basically solve the whole theoretical confusion here, right? Although no one has achieved no one has solved this problem. It's a very difficult problem in not just in computer scientists, but also in mathematics, in theoretical mathematics. Okay, I see a comment here. Mind blowing. Yeah. So, well, for at least here, we will just stick with the common belief that the NP-complete problems are intractable. Okay, so if we describe it, those relationships with some set language, with some graphs, it's basically like there could be several different relationships. For example, if it's indicated by the first guess, it's like P equals NP. Okay, and the co-NP here means that if a problem can be verified, if there's no can be verified no solution, like a counter example, right? So that's just a variation of NP. Okay, so if P equals NP, then it's basically every type of problem are the same. It's like every type of problem can be found a polynomial time solution. Okay, so that is some guess, but it's not very likely though. And the second one is like the P is a subset of NP, right? And C and D are also different types of there's some intersections, right? There's some intersection between co-NP and NP, and the P is just the intersection of these two, right? And the third type, the last type, is that P is only a small subsets of the intersection between P and a co-NP. So actually, most currently people would believe that the D is the most likely. Okay, so that means that only a small set of problems are actually solvable within polynomial running time, okay, according to this guess. And actually, a lot of other problems are not actually solvable. But at least some of them are verifiable. Okay. All right. So typically, we can like summarize the three, if we follow this common belief, we can basically draw a big circle, say that this is all the NP problems, right? So that's NP in the background. That is all the problems that can be verified within polynomial time. And within that, the biggest sets, there is a small set that is solvable, okay? And there could be another small set that is not solvable, okay? Although this is just a guess, and a common guess is that those P and NP completes are wholly contained in NP. I think this is a typo. I think I should fix this. Otherwise, it's caused confusion. It should be NP complete. Okay, it should be NP complete. It should be in the NP, because P, the intersection between P and NP, according to these plots, it should be P itself, right? So the plot indicates that the P and the NP complete, they have no intersections. Okay, so basically we have to, I need to move this to NP complete. Okay, I will do that later. All right. So it comes to the problem, the question of why we do such a classification. And I think there are several reasons other than the scientific exploration, right? Other than the needs to explore the unknown areas in human knowledge, right? It's from the perspective of practices. It's sometimes also necessary, because given an unknown problem, if somehow we can establish it as NP complete, then it basically says that it's intractable, right? If we can prove that, if we can show, or at least find some clues, find some evidence showing that this problem can be an NP complete one, then we basically should give up trying to solve it completely. Okay, right? As an engineer, right, we would prefer to approximate the algorithm or solving some tractable special cases rather than searching for a very fast algorithm that can solve the problem exactly or completely. Okay, so that's is a more practical consideration, right? If we can basically have some knowledge about what type of algorithms what types of algorithms are there in the world, and then we can basically use this category classification to determine how much time we want to spend in and how good we expect an algorithm to be. Okay. So yeah, lastly, I think we're gonna go through some very famous NP-complete problems here. The first one, yeah, the traveling salesman problem, TSP problem, is a very famous one. Okay, so it's like a typical graph algorithm. Okay, it's like a salesman trying to visit n cities, right? And the cities can be viewed as a vertex in the graph. Okay, and a complete graph is a graph that every pair of vertices is connected by a unique edge. Okay, so in this scenario, it's like any two cities on a map have direct flight. Okay, and the salesman can go directly from one city to any other city. So the salesman wants to make a tour or a Hamilton cycle to visit each city exactly once and finish at the city he starts from. All right, so it's just like the Hamilton cycle problem that we talk a little bit about, right? So, and the costs travel from two cities to the other actually is defined, and he wants to also minimize the total cost to the tour. Okay, so that is the some additional constraints placed on top of this Hamilton cycle, which makes it a traveling salesman problem. Okay, So this problem, actually, we can easily prove that it is NP, right? Right. Remember that the concept of NP is that as long as we can verify a solution within polynomial time, then we are good. Okay. Then, okay, so for example, given a solution to this problem, a solution is just a sequence of vertices in the tool, right? So in order to verify it, we just need to go through that sequences, right? And we just sum up the edges, and we will basically need to check whether the summation is at most some value as we determined. Okay, so that's given a solution, it's quite easy to solve, but the problem itself is very hard to solve. And we can actually, people have already actually proven that it is a NP-complete problem. Okay, and the second type of NP-complete problem is called the subset summation problem, and it's actually easier to understand, and actually it's you know, it looks very simple, but actually it's very hard to solve. Okay, so given a finite set of positive integers, and you're also given a target number t. So the question is simply to ask whether there exists a subset, and all the elements in that subset sums to this target number. Right? That's a very easy number. Looks a very easy problem, right? Given a target, we want to determine whether there's a subset that sums up to that number. Okay, and also actually, it's very easy to verify whether a solution, right? You just need to sum up all the numbers, but it's not that easy to solve. Okay, given a solution, we can simply sum up all the numbers within polynomial time, right? So it's very easy to prove that it is within NP. Okay, but actually the problem is hard to solve. All right, and I have two more examples left. The first one and the following two examples are both graph algorithms, and actually they are quite related. Okay. The second one is the first one is called click. Okay. So click is defined on an undirected graph, and it's actually a subset of the graph, a subset of the vertices, and each pair of the vertices is connected within the edge. Okay, so if that's satisfied, then we say this is a click, and the problem is to find a click of maximum size in the graph. So if you look at an example here, the dark blue ones, the four vertices here, it is a click, because if you look at the edges, right, 1, 2, 3, 4, right, there are four edges between any pair. Any one of these four edges actually exists in the graph, right? So that is something satisfy the condition. So that is a click, and this one is also a click. Okay. So the problem is that how do we find a click of maximum size? And it turns out to be an NP-complete problem. It's not an easy one. Okay, but to verify whether a solution is true, then it's quite easy, right? We just check each edge. If there's one edge that breaks the rule, then it's not a solution. If all edges belong to E, then we say this is a solution. So to verify a problem is always easy. Okay, and the second example is called a vector covered. Okay, and this time it's also a subset of undirected graphs, a subset of the vertices of undirected graph. So this time we want to satisfy that if the two ends of the edge exist. So if there are edges that connect two vertices, then at least one of the two ends are selected in the subset. Okay, so basically we want to use the selected subset to cover all the edges, right? So we want to basically find a vertex cover that is of minimum size, and that is the problem defined here. So for example, if we select these two vertices, right, they actually cover all the edges, right? Because if you look at this one edge, it's the one end is included, right? And this one, the one end is also included. And that's true for all these edges here. So that is the vector cover for this graph. And this is the vector cover for this second graph. So we basically select some subset to cover the whole edge. And we want to minimize the sets of this cover. So it's actually related to the previous the click example. So if you look at these two graphs, they actually have the same vertices. Actually, the highlighted vertices here, these two vertices here is the click. Okay, and if you find the complementary graph, which is that you remove all the edges, but you add the connections that don't exist in the graph here, right? Then the vector here, the vector cover is the remaining two vertices, right? Which is which is just exactly the Z and W left it in the first click problem. So these two types of problems are actually closely related. All right, and this vector cover is also a NP-complete problem. All right, I think we are done with all the examples. So lastly, let's look at how to prove the NP-completeness. Okay. So how do we know that a problem is NP-completeness? So actually, we're not required to learn how to do that, but we just will go through this technique a little bit. So it's called polynomial time reduction. That says it provides a formal way to show that one problem is at least as hard as the other one, okay, within a polynomial time factor, okay? So we say that L1, the problem L1 is polynomial time reducible to another problem L2, then we will use this inequality to indicate, okay? We will say that L1 is at least as difficult as L2, okay? And that means L1 is not more than a polynomial factor harder than L2, okay? So we can basically, if we can reduce this L1 to L2, then we can first prove that L2 is a complete problem, NP-complete problem, right? And then if we can prove that's the reducible relationship, then the NP-completeness of L1 is also proven, okay? So it's like to create chains along different problems. And in practice, within this chain of proven, we will basically reduce all the problems into a 3 CNF satisfactory problem. Okay, so for example, the traveling salesman problem can be reduced to the Hamilton cycle, and Hamilton cycle can be reduced to a vertex cover, and the vertex cover can be reduced to a click, and the subset summation, they all can be reduced to a 3 CNF problem, and the 3 CNF problem can be further reduced to some more general problems like satisfactory problem and the circuit satisfactory problem. And as long as we can prove that the circuit satisfactory problem is NP-completeness, then we have proven all the problems below. Okay, so that is a typical way of doing this NP-completeness proven. Okay. All right, and people have actually proven that the circuit satisfactory is a problem, is an NP-complete problem. Okay, so yeah, so last slide here is still some points about what we can do by knowing about the NP-complete problems. And actually, many problems that looks on the surface that's not very hard, right? Actually, they are NP-complete, right? And if we can show that a problem is NP-complete, then we are actually making a statement about how hard it is. It's not about how easy it is. Okay, so we will never try to prove. We are not trying to prove the existence of the efficient algorithm, but instead using NP-completeness, using these concepts, we're actually instead showing that no efficient algorithms is likely to exist. Okay, so yeah, that's so much for the NP-completeness. And let's talk about the finals. Okay,